Okay, welcome back to materials, and today we're going to be talking about stress, strain, and Hooke's law. So your objectives today will be we're going to get through defining stress and strain. We're going to look at how you can determine values, the constants for Hooke's law. And then outside of this lecture, there will be an additional problem showing you how to use Hooke's law to calculate unknown stresses and strains. And we're going to look at how you pull those parameters off a curve. We want to talk about elastic and plastic deformation in materials. And then you should be able to match the regions of different material behaviors with regions on a curve. So we begin with what is stress? And stress is simply the intensity of force applied to a material. And you look at this situation, in both cases we're talking about the same force, 200 pounds. Obviously the intensity is much higher for the poor yellow guy on the right. And so we normalize force divided by the area, and essentially then we end up with a unit that is, or a quantity that is an intensity that tells us what's really happening in the material, even all the way down to the level of the bonds in the material. So how many kinds of stress are there? Well, there's actually three types, two that we will use most of the time. Normal stress occurs when the loads are perpendicular to the face or the cross-section on which they're acting. So see, these forces are all perpendicular. Now, I have tensile forces, which are pulling, and those are going to be called positive forces. And we have compressive forces that are squishing or shortening things, and those are going to be called negative forces. So signs and forces have to do with sense, not direction. Forces will have a positive sign for tension, a negative sign for compression, and so will stress. The stresses that result from those will be positive or negative based on compression or tension. Shear forces or shear stresses are caused by forces that are parallel to the surface on which they're applied. And so in this case, we have all of the required forces. If you know a little bit of equilibrium, if this is a cube, then F1 and F2 must be the same in magnitude, or this cube would spin. Okay, but the point here is, if I take this force, it's parallel to the area. Okay, and the third type of stress is hydrostatic, and that's where you have uniform pressure. This is what you get at the bottom of the ocean, or even in atmosphere. And it's really just of academic interest at this point. You are unlikely to do much with this in this class, but for completeness, we'll give it to you. Okay, so we have intensity of force, force divided by area. We have a similar need when we talk about displacement. And a thought problem here may be most helpful if you think about a string of rubber bands. When if you apply a load to a single rubber band, it's going to stretch some amount, delta. Now, if I put a string together of two rubber bands, apply the same load, each of the rubber bands will extend delta. The total deflection will be 2 delta, and 3, and so on. We're going to have 3 delta here because each one extends the same amount. So obviously, if I talk about the total displacement of these chains, they appear to be very different. But if I think about, well, what's happening to the individual rubber bands, exactly the same thing's happening to each rubber band. So strain is intensity of deformation, and what's the deformation per rubber band? And the initial length of this rubber band we could call L0, and delta, or dl, is the change in length. And so when we combine, originally I had 3 lengths, 3L0, we are going to take 3 delta, divide by 3L0, the 3's cancel. Here we have 2 delta divided by 2 L0s, 2 original lengths, and here delta over 1. So we normalize out the fact that this is a longer structure. So the basic definition of strain is change in length over original length, and this will be your axial strain. Now, when we apply axial strain, when we apply a stress in a direction, you're going to see the body will stretch in that direction, or if it's compressive, then it'll shrink, and you're going to have a lateral response. And so the part, any component that you work with will shrink laterally when you load in tension, and it will expand laterally when you load in compression. And so you're familiar with this as a kid in your high chair. You played with squishing food and watching this stuff happen. So in the longitudinal direction, the total change is, there's two of these u's over 2, the two extensions. Total change in length is u divided by the original length, which is L. And we can also calculate a transverse strain, that is, how much did it shrink, V over 2, so a total lateral is V divided by L. Strain always has units of change in length over original length. And of course that means in the end strain has no units, because inches divided by inches, they cancel, or meters divided by meters, they cancel. Strain is the only number you're going to be allowed to give as an answer on an exam and not have units attached to it. Now let's talk about this lateral expansion or contraction. Materials expand or contract perpendicular to the direction of an applied load. Now, at least in a tensile or compressive load or an axial normal stress situation. Poisson's ratio is defined as the ratio of the transverse strain divided by the axial strain. And we're going to put a negative sign here, because if you think back to this is positive strain extension, so the change in length is positive. Here it's shrinking, so the change in length is negative. So this is a compressive type strain. It's a negative strain. So these two will always, or almost always, have opposite signs anyway. For normal materials, materials that don't violate laws of continuity and energy conservation, those two strains should have opposite signs. So the definition includes a negative sign, so that we end up with Poisson's ratios being positive for ordinary materials. Now, if Poisson's ratio happens to be 0.5, you're looking at a material that is not changing volume. Elastic deformation of materials is not a constant volume process, so you're not going to see this. If you have no idea what the Poisson's ratio for material is, you need it for some minor improvement in accuracy, 0.3 is not a bad guess. Most engineering metals are going to be 0.3. Ceramics tend to be lower, polymers tend to be higher than that, but in the range from 0.2 to 0.35 to 0.4, and with 0.3 right in the middle of all of that. So common good guess. Now, why Poisson's ratio? And anytime we ask a why question, it has to do with, obviously, energy minimization. So we apply a stress. We're going to stretch these bonds. These atoms are going to be separated. Now, they were in their original spacing because that minimized their energy. So if you're pulling the neighbors that are above and below an atom away, the response is going to be to try to pull the lateral neighbors closer to maintain an overall spacing that is about the same. And so it's all about maintaining a kind of constant energy level or a minimum energy level here by maintaining the spacing of the atoms. When this is why, if I have positive strain in this direction, I must have a negative Poisson's reaction here. If I have a negative strain in the axial direction, the Poisson's reaction must be a positive strain, because it's all about maintaining this energy balance. Now, that leads to a question. What would a negative Poisson's ratio material do if you compress it? If you could make a material that violated these laws and had a negative Poisson's ratio, if you compress it, what's it going to do? Well, normally compression means lateral expansion, but that would be a positive Poisson's ratio material. If it's a negative Poisson's ratio material, that means the signs of the two strains are the same. So a compression strain is negative. That means my lateral strain is going to be negative as well. We're going to get contraction, okay? Not something that you are used to seeing. Next kind of strain is shear strain. And in shear strain, we apply shear stress parallel to a face, and that's going to cause a distortion or a change in shape. And shear strain is defined as the horizontal shift divided by the original height. Again, distance divided by distance, so the strain has no units. Now, this is a triangle defined here by that shift, and so we can talk about the tangent of this angle is the opposite, right? W over the height, which is L. So basically, the shear strain is equal to the tangent of this angle that is swept out by the shearing body. Now we're going to find, and one of the requirements for valid strains using these definitions we've covered, is that the strains be fairly small. For very small strains, we have a very small angle. For very small angles, the sine of the angle approaches 0, but as it gets really small, the value is approximately equal to theta in terms of theta in terms of radians, okay? So it's called the small angle approximation. Sine theta, yes, it's approaching 0. But as we get to small angles, we may approximate the value of the function with just the value of the angle. And the cosine theta is very close to 1. And so we're going to be dividing an angle by 1. And basically what we end up saying then is gamma is approximately equal to the angle swept out in strain. Now, that's kind of academic interest, except that you may be reading along in some paper or handbook, and they'll say, we measured a strain of 0.06 radians. And you say, what's that? Oh, okay, the radian's a magic unit. They're reminding me that this strain measurement was shear, not normal strain. So if you see radians, it's a shear strain, not a normal strain that we're talking about. Remember, radians are magic because they tell you you're looking at an angle, but if you multiply the radians swept out by an angle, interior angle in a circle, by the radius, you get the length of the arc. Even though you have radius has length, you multiply by radians. So I should have, inch radians or meter radians, but the radian disappears when you don't want it. It's a magic unit. And so this is nice because it's like strain. Strain has no units. Radian's a unit that goes away when we don't need it. All right. And then there's dilatation, which is simply volume strain, change in volume divided by original volume. Again, units of strain, volume divided by volume, there's no units. All right, so there's our basic stresses and strains. And the point and our target today is to come up with a relationship that connects stress and strain. If I apply a stress, how much strain am I going to get? If I see a deformation and I can calculate a strain, can I determine what the stress is that caused that deformation? And so the simplest rules, or a rule that does that, we will call a constitutive model. It is simply a constitution. It's the law that tells us how something behaves. And a linear model would be mathematically the simplest version of that. And in fact, the linear model we're going to call Hooke's law. And all Hooke's law says is that if I look at how the stress and strain in a material vary, so let's apply increasing amounts of load. Let's divide that load or force by the area to get stress. And let's measure the change in length, but divide that change in length by original length. So now we're looking at strain. And if we're going to get a straight line, at least for the initial part of the deformation of almost all materials, they'll be linear, at least at the beginning. And the slope of this line is, we're going to call Young's modulus. So we end up with a constitutive law. Stress is equal to modulus times strain. Okay? And this is something you just need to know. It's not something that you're going to be given in equation books. You just should know it. So you're going to get the slope. That slope is going to have units of change in stress over change in strain. So units of stress divided by strain, or essentially units of stress. Remember, strain has no units. So modulus is going to have units of MPa or GPa or KSI, or going to be units of stress. Now there's 3 moduli that I want you to learn, and you'll be quizzed on these and be expected to know them. Aluminum, steel, and then an approximate modulus for polycarbonate. Polycarbonate has many different moduli depending on a lot of things, but it's about 500,000 psi modulus. So this is 500,000, which is essentially 500,000, 30 million, and 10 million. And you need to learn those values. We want to give you a few signposts. Steel is an incredibly stiff material. There are not a lot of metals that have a higher modulus than steel. Aluminum is a fairly low modulus metal, and you see it's a 3-to-1 ratio to steel. And polycarbonate is actually a fairly stiff or fairly high modulus polymer. So you see most polymers don't do very well compared to metals in the modulus area, modulus behavior. We have Hooke's law for other types of stresses. So for shear, you have shear strain, shear stress, and the modulus that relates those is called the shear modulus. And fortunately for us, we don't really have to measure it because you can calculate it from Young's modulus, which you get in a tension test, and Poisson's ratio, which you can also get at a tension test. Similarly, we have Hooke's law for dilatation. This would be the hydrostatic problem. And here we call K the bulk modulus. And you'll run into K if you're doing acoustics work because a lot of times the speed of sound in an object is calculated or the equations for that are given in terms of bulk modulus of the material. But again, if I know Young's modulus and Poisson's ratio, we can calculate K. We don't have to measure it directly. All right. So we looked at a stress-strain curve, and we said they start out linear. That is, they're Hookean. But most materials are linear up to some limit we're going to call the proportional limit. That is when it ceases to be proportional. It's the limit of proportional behavior. After that point, we may model the behavior. It may be nonlinear, it may be some new line, and it may be flat. And so these are kind of extreme cases. In most cases, it's going to be nonlinear for some time, and then it may do other crazy things. And we'll look at those things here. Now, when we look at that stress-strain curve, first thing we want to recognize is that there's really two components to the deformation that's going on. The stress-strain curve may be nonlinear, but if I can load the material up and then unload it, and then when I unload, the strain goes all the way back to 0, then I have a perfectly elastic material. Now, in most cases, materials are elastic only over the linear portion of this curve. So as long as I don't exceed the proportional limit, the material will go back to its original shape. Metals are that way, polymers are that way, ceramics are that way. Stay in the linear portion of the curve. When I unload, everything goes back to 0 strain. However, we can also have, with nonlinearity, when we unload, so this would be load up to some high load, stop the test, unload the test. We recover elastic strain, that is, the part relaxes, and we recover the elastic strain, but the strain does not go back to 0, even though the stress is now 0 at this point. This is plastic or permanent deformation. Okay? Now, that's all plastic means for us right now is non-recoverable, and elastic simply means the strain recovers if you take away the stress. Now, this recovery line, if I load up and unload, the slope of that recovery line is Young's modulus. It's the same as the slope of the initial linear portion of the curve. All right, so this is the elastic deformation. We're unstretching the springs in the material, and then whatever's left over is the permanent plastic deformation. Now we need to define an engineering quantity, and this will be the stress that causes permanent deformation. Now the proportional limit is where that literally happens, and we can call that yield. However, and so the stress necessary to do that would be called the yield strength. However, proportional limit can be kind of iffy to find because it just depends on how good your measurements are. And so what we agreed on many, many years ago in the West, and now pretty much everybody does this, is that we're going to allow a certain amount of permanent strain, a strain of 0.002. Also called 0.2% offset. So you can convert strain to percent strain by multiplying by 100. So this is a strain of 0.002, but it would be a percent strain of 0.2. Anyway, what we do is we draw a parallel to the initial modulus line, excuse me, and that's going to have the same slope. It's going to have the same slope as the modulus. And we draw that parallel offset by this amount. Where it intersects, we're going to call that the yield strength, often called an offset yield strength. Okay, we have a problem, though, where we get some unusual behavior in particularly low-carbon steels. We have an upper yield point and a lower yield point. That is, what happens is these materials do not have a lot of carbon in them. And so the dislocations and whatever they're going to move in plastic deformation kind of break loose from where they're anchored. And then a lot of deformation is easy to get before you finally accumulate enough dislocations and the material hardens up to and begins normal hardening behavior. Now, in these situations, it would be dangerous to call the upper yield point our yield strength, because if you're in a design situation, if you accidentally or in service somebody applied slightly larger load, the stress would be higher than this point, and the only way to get a strength that high is way over here. So the part would yield and stretch and stretch and stretch and then begin to strengthen and finally stop deforming way over here, and you would have had this huge amount of strain where you were really expecting nothing to happen. So anyway, we're going to use the lower yield point here as our yield strength in these situations. Now, when you're running a tensile test, and it's possible to do this in the lab, although not a trivial exercise with the way you guys are set up right now. You can start a test and you can stretch the material. You could pause the test and unload. And if you unloaded, the slope here would be the same as the original slope, so that's the same modulus. You get your elastic recovery here. And if you then reload, you'll come back up this line, and then it'll just pick up again where it left off. And so this could be one big smooth curve, but you could stop many times and unload and resume. Now what you notice, if I were to measure the yield strength initially to the offset, we'd get something about here. If we come back to this material, now just pretend if I had run this test, unloaded, and gave you the specimen, you wouldn't know it had been yielded already. And so if you ran it, you would see, all right, let's do our offset yield. We're way up here. We get a higher yield point, same specimen. All right, this points out the fact that when a stress strain curve is sloped upwards after the yield, the material is actually getting stronger. It is taking more and more stress to continue to deform it. And we call that strain hardening. We'll be looking at how that happens or why that happens in a couple of weeks. But that's what's going on when the stress is rising on a stress strain curve. Now, we've identified then a couple of things. If I gave you a stress strain curve, you would get your modulus out of the initial linear portion. You can do an offset to get the yield here. And then, in most metals, we're going to see a peak. And we're going to call that the tensile strength, or the ultimate tensile strength. It's the maximum stress a part can carry in tension. What's happening is, in the elastic regime, we're getting uniform deformation. The specimen is stretching and shrinking. When we start to yield, we still have uniform deformation, but there's permanent involved here, and it's still uniform until we reach the peak, and at the peak, you begin to form a neck. And so this peak load is caused by the formation of a reduced area of neck. And as the load is dropping here, what's happening is we're getting a smaller and smaller cross-section until finally it fractures. And we're going to look at, there's a problem with this. This is an artifact in some sense of us being in tension, but it's a very practical value. The tensile strength, or ultimate tensile strength, is the absolute limit in tension that a part could carry, or a particular material could carry without failure. So it's very useful, particularly in things like chains and cables and guy wires and that kind of stuff. Now, the reason, so this is the process or the mechanism that's going on. When the neck forms, we're going to localize the stress. That is, the actual area that is carrying the load inside the neck is much smaller than the area outside the neck. So you're going to see the apparent drop in the load, and so we see this drop down at the peak. But the reality is, if I calculated the stress in this little neck, that stress is still rising. It is not truly dropping. There's so much less area that we're not going to, that the stress in here is still higher, even though out here the stress is dropping because the load was dropping. You're only going to see this peak in tensile tests, not in shear tests and not in compression tests. It's an artifact. It's caused by the formation of a neck in most cases. All right. Now, what happens in that neck is, and we need to recognize this, if we look along a test specimen, and so here we're looking at the amount of strain on the specimen along the gauge length. And so as we start up, we get to yield. The deformation or the elongation everywhere along the specimen is the same. You get to point B, it's still uniform. At point C, it's still uniform, but as we pass C at the peak, we have started to form a neck, and now what's happening is the strain outside the neck isn't changing. So outside the neck here and here on either side of it, I'm still at the same stress I was at point C, even at point D and point E. But in the neck, the strain is rapidly increasing, and as we get to fracture, we have dramatic amounts of strain inside the neck. So it's a localization of the deformation in the specimen once the neck starts to form. Okay. Now we have some other things that we like to do. Because of that localization, we're going to see a reduction in area. And so The percent reduction of area is another way to kind of estimate how ductile the material is. You take the original area minus the final area, divide by the original area, multiply by 100, and you get a percent reduction of area. And this is a measure of how much plastic deformation the materials experience. And the nice thing is you can easily do it with broken pieces after a test. You don't have to be measuring during the test once the neck is formed. Now, the other measures we want to pull out of the stress strain curve are the strain to failure, and there's two elements to that. There's the total strain at failure, which includes both, let's say this had broken at this point. If we had stopped and unloaded, we would have had elastic deformation at that point of failure and plastic deformation at that point of failure. So the total strain at failure, we would just read straight down. That's what it was when it broke. We can then draw an imaginary line parallel to the modulus, and from that estimate, well, how much of that strain was permanent or plastic deformation. Okay, so this is an estimate of kind of ductility, and it's comparable to the reduction of area. So they're both telling us similar things. In fact, this should be proportional. The plastic component particularly should be proportional to the reduction of area, which is a measure of plastic strain in the lateral direction. So everything that you can pull out together on a stress strain curve, and we're going to have a separate video. We'll walk through calculations of all of these things with you, as well as obviously we're going to be doing this in class. So you have the modulus. You should be able to pull off the initial slope, offset 0.2%, or a strain of 0.002, depending on what your axis is. If your axis is strain, you're going to be 0.2. If your axis is percent strain, you're going to use 0.2. If your axis is strain, you're going to use 0.002. But you'll offset, draw the parallel. There's your yield strength. Onset of necking here, your peak. That's going to be your ultimate tensile strength. Final fracture, there's your strain at failure, and if you follow this parallel to the modulus line back, you're going to get your plastic strain at failure. Okay, so those are all the things we should be able to get out of a stress strain curve on one slide. Now, there's different kinds of stress strain curves. Shapes can vary widely. The ones on the left are metal and ceramic curves, and then the ones on the right are polymer kind of curves. We'll see with polymer, so we don't really talk about these right now. But the simplest would be something that's just linear, elastic, and then it breaks. There's almost all of your ceramic materials. This is classical metal behavior, and then this will be low carbon, some of the low carbon metals, and then some of your FCC metals will give you fairly low modulus, very low strength, and tremendous strain to failure. Okay, so those are kind of the different curves you may see. In all cases, we can measure a modulus. In all cases, we've got a yield here. We've got the lower point yield here. You have offset yield there. And yield doesn't mean anything here. This is brittle fracture. So the only strength you'd report here is the peak stress. Now, stress strain curves are influenced by a lot of things. The two biggest things that we have to worry about are temperature and the speed of the test, or the strain rate. And so if we look at a stress, this is stress strain curve as we change the temperature. As you lower the temperature, going from T1 to T2 to T3, we're lowering the temperature. You're going to see in most materials a rise in the stiffness, a rise in the yield strength, and usually a reduction in the strain to failure. Now, for metals, this effect is not particularly strong, and from 0 to 100 degrees C, you usually won't see very much change in the stress strain curve. So over ambient conditions in which people live, metals are fairly constant in terms of temperature. Polymers are highly sensitive, and metals, over large temperature ranges, you will see this behavior. Same thing happens with speed of the impact or the testing, speed of loading. And so at the lowest speeds, we're going to have a lower stiffness, a lower strength, and a higher strain to failure. And as the speeds get higher, we're going to see higher yield strengths, higher moduli, and lower strain to failure. And those again apply. Again, metals are much less speed sensitive. We'll be playing with silly putty in the plastics when we get to the polymers lectures. And it's highly speed sensitive. But for a lot of metals, we don't see a big change in the stress strain curves until you get into the truly dynamic range, such as 30 to 60 miles an hour kind of loading rates or strain rates. You can do interesting experiments where you start the test and then change the strain rate, and you can see this hopping back and forth between the two curves that it is trying to, or would follow if it was running at a single speed. All right. So you should be able to answer a couple of questions. Elastic deformation is recoverable, true or false? And that should be true. That's the basic definition of elastic. Most engineering materials have a Poisson's ratio value near n.3 is a very good guess for most structural materials anyway. And finally, can you calculate stress? Put 16,000 pounds on a 2x2. Stress in KSI is going to be 16,000 divided by the area, which is 2 times 2, which is 4 square inches. So you should have 4,000 PSI, which is 4 KSI. Right? All righty, that concludes the basic introduction of stress, strain, Hooke's law, and stress strain curve.